Today, we are very much fortunate to have a paper that will be mainly methodological and econometric in nature, combining developments in econometrics as well as developments in finance. And so, today we have an icon, indeed a distinguished researcher, Professor Abderrahim Taamouti, whom I've had a great pleasure of interacting with, in the part of the Economic Society. And he did, yes, indeed, convene the African region a meeting a couple of years ago, maybe 2 or 3 years ago, or 2 or 3.
2019, yeah.
Yeah, 2019, yes, which was a great meeting. But just to, again, his CV is so strong, I would possibly spend an hour reading, but just to be very precise, he's currently a professor of economics at Durham University. And he took his PhD in 2007 in economics from University of Montreal in Canada. And the journey from Montreal to Durham had to go through a number of stopovers. He first of all held the position of associate professor of economics at Universidad Carlos II de Madrid in Spain. And then finally before moving to Durham. His field of specialism are econometrics and finance, and has worked on a number of very interesting topics, like Granger causality, hypothesis testing, non-parametric estimation and testing, asset pricing, and portfolio theory and selection, and risk management, which is actually what the paper today is addressing, with a lot of applications to even bank management. These are the measures which are tools which are applied widely. And he's very, very prolific guy, has made a lot of contribution to high esteemed journals, including in econometrics, finance and statistics, like Journal of Econometrics, Review of Finance, Journal of Multivariate Analysis, Journal of Dynamics and Economic Control, Journal of Financial Econometrics, Journal of Business Economic Statistics. I could go on and on and on, but he's definitely hitting the top-notch journals as part of his prolific research in both econometrics and finance, or even a combination of economics and finance, which is the financial econometrics with application to banking and many areas of economics. So it's a great pleasure that we welcome you here, Abderrahim, to take us through the various risk and methodological concerns that are of high applications in many areas, and therefore giving a new thrust to researchers at various dimensions of the cycle, from early career researchers to established researchers. So the floor is yours.
Thank you very much, my friend Victor, for this very kind introduction and generous one. Thanks a lot. Thank you very much for that. And I must say that that the great conference that we organized in 2019, maybe without your help, it would not. I mean, maybe we'll not have it, because I remember how much you were involved, at high level, either in the Econometric Society or even in locally there in Morocco, like to help and make it take place. So thank you very much for that, and it's really a pleasure, and thank you for inviting me. So maybe I should add that that I mean, my journey continues. So I've been in Liverpool management school starting from January. So I'm getting a bit close to London. So
okay.
so yeah, so
Okay.
yeah. But that's until 1st of January. So thanks a lot again, everyone, for coming to the presentation. So today I'm going to present something, as Victor said, on management, risk management. So that's what we call value at risk. And the topic of today is about how we can calculate or how we can estimate value at risk when the prices, for example, are contaminated. So there is a measurement error in the price. I must say that this is, this is the I would say the only paper on that provides some methodology on the estimation of value at risk when the prices are contaminated or when there is a measurement error. And this is a joint work with Mohamed Doukali and Charles Janson. So, so I guess you can see my slides. So the outline of my presentation. So I'm going to start with the motivation. So why this is it's worth investigating this problem, and then I will try to summarize my contributions. Just to make sure that I'm on time, and at least you get the picture of what is in this paper, and then I will discuss the framework. So that's the framework that we're going to use to estimate or calculate the distribution function of the unobserved true portfolio returns. So the idea here is that you have prices. I mean, all what you observe is a price that is contaminated. And so now how we can recover, the idea is how we can recover the true prices or the true portfolio returns if you have a portfolio. And in particular, how to recover the distribution, because as you know, the value at risk is nothing else than a quantile. So if you know the distribution, then you can invert the distribution to get the value at risk. And then I'm going to show you how to, again, invert the distribution to calculate the value at risk under measurement errors here. And then show you some Monte Carlo simulations to, investigate how our methodology work in some scenarios. And then I will end up with, explaining an empirical application where we apply this methodology to five international indices. So again, the motivation is, as you know, the value at risk is one of the most widely used techniques or measures to measure the risk of loss for investment. So we have value at risk. We also have expected shortfall. So here I focus on value at risk, but we have we are currently working on an extension to expected shortfall and how to apply this methodology to estimate expected shortfall in the presence of contaminated prices. And the value at risk, I mean, just brief reminder of the definition of the value at risk. I mean, the value at risk is just a quantile in the quantile of a distribution. So it is a quantile that measure the worst expected loss over a given horizon. I mean, typically, as you know, the banks are supposed to report the value at risk. I mean, to calculate that either at daily or weekly horizon, so they can know how much they should leave of capital, like our capital, because we have our saving in the banks, aside as a protection of our savings. So that's at given horizon and also at given statistical coverage rate. So if you want, like the worst case scenario, so if if the markets, let's say, I mean, collapse at some certain level at 5% or 10%. So that corresponds to 5% or 10% quantile. So given its importance, so financial managers, bankers are, I mean, the regulator also, I mean, the central bank is concerned about the precision of value at risk, because if we get that wrong, especially if we underestimate the risk, then that means, of course, our saving is at risk, and also maybe it could be also a collapse of the financial system or the banks, and we know what that means when we look at Lehman Brothers case and the consequence of that. So this estimation, as we show in this paper, can be affected by the presence of measurement errors. So measurement errors, as I said, is like you have a price that is contaminated, and this can be caused by many issues. Could be like non-synchronous trading, rounding errors, and frequent trading, market microstructure noise, manipulations, etc. So all this can affect the prices, and we may end up observing a price that is completely different from what we call the efficient or the true price. So that's the idea. So the idea here is to provide a methodology that can help you estimate the value at risk in the presence of contaminated price. So now I'm gonna discuss a bit the framework that we're gonna use to develop our methodology. So here to develop our methodology, we follow the finance literature, as you know, and consider what we call the additive measurement error model. So that, if you look at the literature, for example, on high frequency data, or like the literature on volatility estimation using, for example, high frequency data, etc. So they consider this type of models. So where, I write it here in terms of return, but you can also write it in terms of price, as I will show in a minute. So where you have the observed, what you observe as a return when you get Excel file of data from either like one of these databases of finance. So what you get, so you have a return that is equal to the contaminated return, which is the true one. So this is the observed one, and this is the latent one, or the unobserved one. And so what happens is that the unobserved one is contaminated by a measurement error E here. So as I said, this is the model that is considered in the literature to investigate the impact of contaminated prices on the estimation of volatility. So what I can say is that there is a huge literature on investigating, or if you want, providing robust estimators of volatility under measurement errors. I cite few papers here, like Eid Sahali and co-authors 2005, Bundy and co-authors 2006, but there is a big number of papers that we can cite. However, unfortunately, if you look again to the literature, there is no paper. As I say here, no attention is paid to the effect or the impact of measurement error on the value at risk estimation. So we look at its impact on volatility, but there are no papers on how this measurement error affect the estimation of value at risk, which is, of course, important, because again, as I said, this involves our saving. This involves the safety of the financial system, and so thus no robust estimation technique is available in the literature that provides estimation of the volatility, or the value at risk under measurement error. And that's what we do here. So just to illustrate a bit, I mean, I would say this is a sort of like theory here. I mean, just to illustrate a little bit why measurement error could affect the estimation or could affect the value at risk when the value at risk estimation when you use observed returns or observed price that are you know, contaminated with some error. So here in this graph, sorry, yes, let me try to put it a bit bigger. So what what I do here in this, so this is a convolution, if you want, of the right-hand side tail of the distribution. So you can imagine a symmetric distribution. So I'm looking at the right-hand side, but what's happening in the right-hand side is exactly what's happening in the left-hand side. So if you are interested in value at risk, but anyway, I mean, I should normally present the left-hand side, but it's similar here. So what we have is, you know, I think I should. So we have a convolution. So we have the observed return. So the observed return is the curve here in the middle. So this is the right hand side tail of the observed return, and that's equal to the contaminated return. So the contaminated return. So that's why I'm trying to, you know, make this figure bigger. So the contaminated return is this guy here. So what we do, in fact, so to generate the observed return, I just say, okay, assume that we have that the microstructure, let's say the measurement error is given by normal distribution. Okay. That corresponds to the dashed line. So this is the normal distribution down here. That represents the measurement error. And then let's assume, but you can play with that, of course, you can consider other distribution. And let's assume that the true return, the latent one, is given by student t distribution with 3 degrees of freedom. And that's sorry if you can't see it, but that corresponds to this line, almost invisible one here. Right? So now if you do the convolution of this line with this line here, that gives you the observed return. But that's, you know, so that's what happened, if you want. And now what you can see, so now if you compare the tail, because that's we need the tail to compute the quantile, so to compute the value at risk. So what you see here is that the tail of the unobservable return dominates the tail of the observed one here. Okay, so what that means, so for example, if so you have more mass you know, let's say mass probability here in this one here than in this one. So for example, if you say I want to estimate 5% value at risk, so 5% value at risk for the using the unobserved return that you don't observe, of course, you know, because it's fat tail. So the 5% maybe, let's say maybe is around 12, just for illustration, right? And because the unobserved one, the observed one is less fat, you know, there's less fat tail in the observed one. So the 5%, you need to move somewhere here, right? So that will be the value at risk based on the observed return. And this here will be the value at risk based on the unobserved one. So what happens if you, when you use the observed return, your estimate will be somewhere here of the value at risk. So you will end up underestimating the risk. So you're underestimating the risk, even though the risk, imagine from the left-hand side, so it will be more negative. So that's an issue, of course. So that's I hope it's a bit clear. So I mean, to summarize here is that I mean the right tail of the density of the unobserved return dominates the right tail of the density of the observed return, and that similar thing happening in the left-hand side, because I'm talking about the left-hand side because that's what we use to estimate the value at risk. So I hope it's not confusing showing you the right-hand side. So hence, I mean, the existing estimators of value at risk that are, that only use observed returns, they will ignore the measurement error, and they will lead, as we just saw with the simple example, they will lead to inconsistent estimate of value at risk, and in particular will lead to underestimation of risk, which is problematic, because I mean the bank will estimate a value at risk thinking that the risk is low, so putting less saving aside to protect our less capital aside to protect our saving, whereas I mean the reality is that that risk is much bigger. So they put at risk our saving and of course themselves. I mean the bank itself is putting it's at risk. So hence providing robust estimation methods for value at risk under measurement error should be extremely important for risk analysis. So I can stop here for a minute just in case if you have any question, or otherwise, yeah, I'm happy to continue.
Yeah, that's all.
Okay.
Go ahead, yeah.
Fantastic. So, okay, so to summarize a bit my contribution, just in case if I miss my time, so we develop a semi-parametric estimation approach for value at risk when the stock price are contaminated by measurement error. So in particular, I mean semi-parametric estimation, because as you're gonna see in a minute, we assume we have to make an assumption about the distribution of the measurement error, and that will be a parametric, like assuming a parametric distribution, and in particular normality of the error term, or the measurement error, but we go non-parametric for the observed return. So as you will see in a minute, we will need these two components to get the distribution of the unobserved return or unobserved portfolio return. And so because we have parametric and non-parametric, so that leads to a semi-parametric estimation. So what we do, as I said, so the derivation, as we will see in a minute, the derivation of our robust estimator of value at risk is made under the assumption that the density of noise is known. Of course, that's in practice is nonsense, but just to illustrate a little bit how the methodology works. But then later we will relax this assumption by assuming the noise is normally distributed, but with a known variance that we can estimate from high frequency data. And I should mention here that maybe here I'm assuming normality of the measurement error, but that doesn't affect what we know in practice, because we know in practice that the observed returns are non-normally distributed. So, but please remember that here, I'm not making any assumption about the distribution of the observed returns. So the observed returns can be anything, normal, non-normal, any distribution, right? We go non-parametric. And we go parametric for the distribution of the measurement errors. In particular, we assume normality, but combining the normality of the measurement errors with, let's say, normality of the observed returns to recuperate the distribution of the unobserved returns makes the unobserved return distribution, I mean, can be anything. I mean, not necessarily, it could be normal, non-normal, or any other distribution. So the approach here, I'm repeating this because maybe some people could be confused saying, oh, we have an assumption here, normality of the measurement error, but that has nothing to do with the, for example, non-normality of the returns. I mean, returns can be non-normal. And more than that, I should mention that, the methodology that we that I'm presenting here can be also, redone for any other distribution than normal for the measurement error. So, I mean, in particular, if you give me the characteristic function of the measure, any characteristic function, let's say analytical one for measurement error, I can develop in a straightforward way same calculation as we have here. So just to say that the normality, even for the measurement error, is not restrictive. So once we develop the estimation of value at risk, or the robust estimation of value at risk, then I will show you some Monte Carlo simulation where we examine the performance of our approach. So the performance here, because we are talking about estimation, so naturally we have to look at the bias, at the standard deviation, and the mean square error of our estimator. And what we do, in fact, we also compare this to a model-free, let's call it in this way, a model-free estimator that doesn't adjust for the measurement error. So we take a model-free just to make sure that there is no effect of the model on to have a fair comparison with our estimator. And then at the end, I will present, show how we can apply our method to estimate the value at risk of 5 international market indices. So now let me get a bit more in detail. So here I'm considering an economy with n risky assets. So I denote PT here, the vector of the observed log prices at time t, so that we have n assets, so we have n prices, and all these prices are observed. So that's what you observe in the data. And then I will denote the unobserved one, or the latent prices, the true ones, by P1 T star until Pn T star. So that's to distinguish between observed and unobserved. And so what we assume here is, we assume that the observed price is contaminated. So the observed price is the true one plus contamination or measurement error. That we assume is IAD with some given variance sigma epsilon square. So that's for the prices, but we can use this equation for prices to move to the returns. So again, we make this assumption that the vector of contaminations or measurement error is independent of the true observed return. So we assume that these guys are independent. That's a very classical assumption in the literature of finance. So there is nothing new here. And then furthermore, the density of epsilon, I mean, for a moment, but we're going to relax this later. We assume that the density that we denote F epsilon, we assume it's known with, let's say, variance, with the normal distribution, with the mean 0 and constant variance. But we will relax this assumption later. And again, I do the calculation here in the next slides for normality. But if anyone is unhappy with normality, even though it's quite what is considered in the literature, just give me another distribution, or in particular, give me the characteristic function of the error term. I will do the same calculation here. So yeah, I mean, from this we can easily move to the observed. To the observed and latent true returns. So this is the observed returns. We denote this is the observed return for the asset G at time t, and this is the unobserved one at time t again of the asset G. So it's straightforward to see that we can have this equation for returns. So the observed return equal to the unobserved one plus the contamination. But now the contamination, which is the difference, because the return here is just the difference of log prices at t and t minus 1, so it's just the double I mean, the variance of the new noise is the double of the noise that we observe in the stock price. And again, so that's a remark that I made before. We are very general about the distribution of the observed and unobserved stock returns. So there's no, I mean, normality doesn't restrict, let's say, generally speaking, the distribution of the observed and unobserved returns. Then from this we can move to the return of portfolio. So given that we have an asset, so we can consider this portfolio. So this is the portfolio return. So this is the observed one. The observed one is just the weighted return, the weighted returns of the individual assets. Okay, so this is the weights W1 to Wn. Okay, so now from this, if we combine this equation 1 with this equation 2, it's straightforward to see that even that the portfolio, the observed portfolio return is again can be written like for the price. I mean, like the equal to the unobserved one, the unobserved portfolio return plus the contamination. Here now the contamination is a weighted sum of the contaminations from the stock return, the individual stock returns. Right, so that's sorry, I'm just a bit panicked here because I think I have my team for my university is open, and I think there is a meeting now. And so do you is it the noise bothering you, or
no, we don't
you don't hear that?
Anything in the background, so you're fine.
Ah, okay, fantastic. But if you hear any noise, I can maybe, I guess if I close my Microsoft Teams for...
No worry, if I hear anything, I'll let you know.
Okay, good, thanks, fantastic. So yeah, that's it. So we have this observed portfolio return equal to an observed one plus the contamination, as again the contamination here is now weighted, and the weighted noises that microstructure or measurement errors that comes from the individual return here. Okay, right. So now we have the basic. So now the idea again, please remember that the target here is to recover or to estimate the distribution of the unobserved portfolio return. I mean, what I'm targeting here is to get the distribution of the unobserved, this guy here, the unobserved portfolio return. So once I have that, once I have the distribution of this guy, I can invert it. If I invert it, then I will get the value at risk. So now in the next step, let's work to get the distribution of this guy. How are we gonna do that? We're gonna use the distribution of this guy and the distribution of this guy. That's a sort like this is a convolution. So that's what I'm gonna do. So I'm gonna work with the characteristic function. So as you know, if you have having characteristic function is like as if you have the distribution function. Okay. But as you can see, the calculation here are straightforward for the characteristic function. So what I'm going to do, so I'm going to use this equation here, and I use the fact that this guy is independent of this. So then the characteristic function of the observed portfolio return will be equal to the characteristic function of the unobserved one time the characteristic function of the measurement error. That's what we have here. Okay, that is straightforward from here. Now, so remember that I'm after this guy here. I want to get the characteristic function of the unobserved return, because once I have that, I have the distribution, and then I can just invert the distribution for value at risk. So now, obviously, I can get this one by dividing this one by this one, okay? But before doing that, so let's ask the question, what is this guy? So I need to get this guy and get this guy here. So let's start with this one. So this is straightforward. I mean, we know what is this is the measurement error. That is a sum of the individual measurement errors. So its characteristic function is easy to calculate. So it's given by this expression. So this guy here is what we have here. That is because the individual measurement errors are independent. So I can write it as a product. Okay, that's what I write here. And then if you say, as we do here, you tell me that this guy is normally distributed, then we can have an analytical expression for this guy that is given by this. So that's the characteristic function of the measurement error in the portfolio, right? Under the assumption that the measurement errors in the price are normally distributed. So that's easy to, you know, see that that's the expression of the characteristic function. Now I worked out this guy. I need this guy now to recuperate this guy. So this one I just go no parametric. So this guy make a parametric assumption normality, but this guy just say I don't know its distribution, and then I estimate it using an empirical analog estimator. So this is the mean of the characteristic, the average of the characteristic function, the sum that we know, and that gives me an estimator of the characteristic function of the observed portfolio return. Okay, that's something that we all can obtain quite easily. Now, you know, I go simple here, but maybe some of you may be interested to use other estimators of the characteristic function. We have a lot. I mean, you can use some sort of like kernel based estimators. There are many available estimators in the literature, so you don't need to restrict the estimation to this type of estimators. And as you will see that maybe if you just take another estimator that is based on kernel, like smoothing, for example, as I will explain a little bit later, that could help you avoid this smoothing here that I will explain in a minute. So you could either do it here or either here. So here I'm not smoothing, so I'm using the empirical estimator instead of like sort of kernel based estimator. But you can do it. You can do it if you wish. So now, combining this and this, I can get this. So that's it here. So it's this ratio that I can write like this. So that's the estimator of the characteristic function of the unobserved true portfolio return. Okay. The problem with this estimator, as I just explained a minute ago, it's maybe not smooth, and we can show that it's not integrable. Okay, so when it comes, for example, to inverse, because you need to move from the characteristic function to the distribution, you need integrals, etc., and you might have some problems when you use this guy here. So in that case, what we do, and again, as I said, we can do it here before, we smooth. So we consider some regularization of this guy here. So using some kernel, Fourier transform kernel, this guy. So instead of only using the ratio, we multiply it by this kernel, which is this Fourier transform of some kernel function. That depends, of course, on some bandwidth. So, I mean, the choice of the bandwidth here, we will be inspired from these two papers for the choice of the kernel and the bandwidth. And in particular, in fact, for the kernel, for this kernel, and inspiring from this paper, we pick this kernel function, which is y here is a designating indicator function that we can also write. It has the following form: sin over px. Anyway, this is you could consider other kernel functions, etc. Now we have the characteristic function. Then we can use this theorem, right? I mean, we can use the Fourier inversion formula. You have different ones. So we use the one in Gill and Pilasse 1951. So then from the characteristic function of the unobserved portfolio return, we can have the distribution. So that's the distribution of the unobserved portfolio return for its value at a given return, unobserved return RP star. So that's the expression, which, I mean, once you replace this guy here, remember the expression is here, or in particular is here. So if we replace this guy, which is given by this, here we get this expression. So so you see, we are quite close now to the value at risk. So normally, if you have the distribution function, you can just invert it to get the value at risk. I mean, one remark. I mean, this guy here, you can write it as a kernel. I mean, in terms of kernel expression. So this guy, in fact, you can write it in this simple way, and this L is given by this one. So it's nothing else like a sort of kernel function, which I mean is that's what we call the deconvolution kernel, and the B, again, as I mentioned before, is a bandwidth parameter. Now we're going to use that, as I said, to estimate the value at risk and under the measurement error. So because we work here with the unobserved portfolio return. So for the value at risk, so as you say, I mean, as you know, so let's denote the value at risk as in paper. So VR. So that's the VR of latent true portfolio returns at given nominal coverage rate alpha. So that's how we denote it. Okay, and that's supposed to be positive. Okay, the measure of risk is positive. But because we work here with the left-hand side distribution, the left-hand side of the distribution, so what I mean, the quantile will be negative. So that's why I add minus here. Okay, so that's what we have this expression. So this expression. So all what I do, I replace this guy here or here, right, inside by the value at risk, and that I get this expression here. So that's so what you have an equation that is a function of value at risk. So the question now is how we can estimate the value at risk from this equation. So again, as I said, this is about inverting the distribution function. Yeah, so that's what we're gonna do. So that's we have in this proposition. So the value at risk of, I'm just writing it a little bit formally. So the value at risk of latent true portfolio return at a nominal coverage rate alpha that we denote by this is the unique solution for the following expression. So the value at risk, you can obtain the value at risk by solving this equation here. Okay, and this equation, in fact, it comes from this. All what I did, because I'm interested in value at risk at 5%, so I say the distribution, the cumulative distribution equal to 5. So once you replace this cumulative distribution by alpha, because that's your targeted coverage rate, then you have this expression. You can write it in this expression. So unfortunately, this is an expression that is very nonlinear. So we can't solve it in an analytical way. So we cannot isolate the value at risk in an analytical way. So that means we need numerical expressions to solve this. You have to do it numerically, not by hand. So that's one way of solving it. Or if you prefer, you can write this problem as a minimization of a quadratic function. So the value at risk will be a minimization of this term here. So this term again is this guy here, right? Just square it, and then you say the value at risk is the one that makes this term square close to 0. I mean, theoretically, it should be equal to 0. So you minimize that. of course, that's now the calculation. I mean, the estimation here is not that straightforward. And because the problem is that we have this integral, so infinite integral from 0, 1. And so the exact solution will not be feasible because of this expression here. And so what we do to simplify that, we replace this integral by sums using what we call, sometimes we call it series representation. So you can consider series representation of sine and exponential functions, and if you do so, then you end up with this expression. So you get rid of this integral and you replace it by some sums. So then we have this expression again. So the value at risk of latent true portfolio return at a nominal coverage rate alpha that we do not by this is the unique. So in fact, we can show that there is one and only one solution for this equation. And it's quite simple to see that, because here we work with the distribution function, and the distribution function, it has some properties. For example, it's increasing, and because it's increasing, if you think about Newton, numerical techniques. So it's like you search for, for 0, where this, it's like you minimize that function, but it crosses, because it's monotonic, more or less, it crosses the line of 0 once. So there is one unique solution for that. So that's what we're gonna use. So the problem again, but we face another problem here, is we have an infinite sum, and we need to truncate that sum. So truncation, so what we do, so we write this sum here, right? This sum, we write it as a sum of two elements. So the truncated term that we're gonna use in practice, and there is a reminding term that is, if you want, that we need to control, that is the truncation error. So the term that we use in practice, so we replace this guy here by this term, okay, with the limited L and K, okay. So now, of course, the question here is, what's the best L and K that can make this truncation error close to 0? Or is 0? I mean, maybe we cannot reach 0, but maybe how to minimize this L and K. I mean, we spent quite a lot of time to see whether we can find a theoretical solution for the choice of L and K. So if you want to, just to give you an idea, we were able to decompose this term to 3 terms that are expressed. I mean, they look a bit messy here, but they are not that difficult to understand. But these 3 terms are like parts of this truncation error. And in fact, we can quite easily bound these error terms as this. So they are bounded by this expression. So they are all in absolute value smaller than this expression. So we tried theoretically to see what L, I mean, for example, someone can say, I want these I want each of this to be 10 power minus 10. So very small. So the question here is, what is L and K that can make this guy 10 power minus 10, this guy 10 power minus 10, this guy 10 power minus 10? Or I just give an example, but could be 10. Someone could be satisfied by 10 minus 3 or 10 minus 2 or something like that. So, I mean, we tried, I mean, maybe we didn't go until the end. We tried to see whether we can solve these inequalities for L and K, and they were not quite straightforward. So all what we were able to show is that these guys, obviously, these 3 terms are, they converge to 0. More L and K you take, larger L and K you take, you're gonna make these three error terms close to zero. I mean, that's obvious. So hence the total term truncation error will be zero. But anyway, we try to find L and K theoretically for some given values of these guys. We were not that successful, so we had to give up and then use simulation. So in the simulation, we ask the question, what could be for some, models that we consider here, what could be the L and K that can make these guys negligible? So negligible here in terms of bias, mean square error. So what we find, I don't want to go in details because that could take quite a lot of time. What we find is that the taking L and K equal to 10 here, you take these guys equal to 10, yields to satisfactory results in terms of bias, mean square error, etc. So that's how we do it. So now, yeah. So I'm sorry, if I'm not stopping. So if you have any question, I can take and have time also to drink a bit of water. But otherwise, I'm happy to continue. Yeah, fantastic. So now for of course, remember I made an assumption here at the beginning, assuming that the error term is normally distributed with known variance, right? As I said, of course, that's in practice is not a practical assumption. So of course, the variance of the noise is unknown. And so what we do, we use some papers from high frequency data literature, some high frequency approach. So for example, if you look at this paper by Aitzahali and Kothor in JAZA, so they provide an estimator of the variance of the noise. And that looks, of course, we had to adapt this for the portfolio. That looks like this expression here. That's, of course, it's quite, it's a sort of like realized volatility expression. So where we have this is the prices at intradaily prices. So for example, you have a day from, let's say, day from 0 to t, and you observe all these prices within the day. So you can use that to get an estimate of the variance of the measurement error. So that's what we use in practice. So now I think I covered more or less the theory part. So I'm gonna now move to the Monte Carlo simulations. So what we do here, we do a simulation exercise where we ask the question, how is the performance of our estimator or the approach that I just presented compares to like the approach that ignores the measurement errors? And that's what is now in the literature. People, when they estimate the value at risk, they completely ignore the measurement error. So so for the simulation, what we do is the following. So we consider this model here that I showed before. So this is the observed portfolio. You could see this as portfolio return, which is equal to the unobserved portfolio return plus the contamination or the measurement error. So what we do, we say, okay, the measurement error is correctly specified. So is normal 0,1. We just for simplicity focus on normal 0,1. And then what we do for the unobserved portfolio return, we simulate that from different models that are used in the literature, like for example an ER process or an MA process or GASH11 process. And so of course this guy will be generated from this, right? This guy will be generated either from this or this or this. So once we generate both, we sum them, then we generate the observed return. So that's what I'm saying here. We then use equation 10 to simulate the observed returns. So once we have that, in fact, because of these assumptions here, it's straightforward to calculate the value at risk analytically in this case for each of these models. So we can use each of these models analytically to calculate the value at risk of the unobserved portfolio return. So of course, this is a simulation exercise, so we know the truth. So we know the true value at risks. And then we're going to use that to calculate the bias of our estimator, the mean square error of our estimator, and of course the standard deviation of our estimator, but also the bias, mean square error, and the standard deviation of the what we call unadjusted estimator that doesn't take into account the measurement errors. So that's what is provided in the table here. So this is the actual value at risk at 1%, 5%, 10% of the value at risk of the true portfolio return. So using either ER1, MA1, and GOSH. So this is for 1%, this is 5%, and this is 10% used for the three models. And now next is to use these values to estimate the bias, standard deviation, and the mean square error, or the root mean square error, for our estimator and an unadjusted one. So the unadjusted estimator, because we don't, as I said at the beginning, because we don't want, we want to be fair in terms of comparison with the approach that doesn't take into account the measurement error, we just go non-parametric. So what we do, we take the observed return, and then we use the empirical distribution of the observed return. I mean, we invert it, okay, to get the value at risk that we call unadjusted one, because it doesn't adjust for the contamination. And then for our approach, so remember that for our approach we need this truncation, LK, that's what we take 10. And we need some bandwidth. So if you remember the expression, I had some bandwidths. So the bandwidth, we take this from Atsu and Taylor, 2017. So we consider, so that's the bandwidth that they take. We take the same, so the rule of thumb. And we consider this bandwidth for different values, 1, 1.5, 2, 2.53 of C. And we do this exercise, I think we do it for 3 samples, not only one. Let me just check. I think we do it for 125, 250, and 500 observation instead of 2. So there is a typo here. And then we consider 1,000 replications to estimate the bias, mean square error, standard deviation. So let me, Victor, how am I doing in terms of time, right? Is it okay, or?
You are doing okay.
Okay, fantastic. Okay, so but anyway, I'm getting close to, yeah. So now, so let me give you a bit the picture of what we do in the simulation. So you understand that we look for the bias, mean square error, and of course the standard deviation. But we consider 3 different scenarios. So the scenario 1, where we consider that the distribution of the measurement error is well specified. So there is, I mean, we use normal 0, 1, and it's the true distribution. The second scenario that I'm sure many of you will ask, the question, what happens if you use for your estimator, you develop your calculation here, assuming that the measurement error is normally distributed, whereas in reality that measurement error is not normal. It could be like a mixture of normal, or it could be mix a student, etc. So what happened to your estimator? Is it going to be good, or? So that's the scenario, the second scenario. So we also provide simulations where we say, look, we do the calculation under normality, but the measurement error is either mixture of normal or a student with 5 degrees of freedom. So completely different distribution than normal. And then we provide the performance of our estimator. And the last scenario is where we say, okay, I mean, what if there is no measurement errors? So is our estimator still perform, you know, quite good or nothing? So that's the third scenario. So the case where no measurement error is there. But anyway, I think showing you the tables of simulation is, you know, it's quite, I have maybe 16 or more than 16 tables. But so I could summarize this. I could also combine showing the tables a bit. But the idea here is we look at the performance of our estimator and we compare it with the unadjusted one in the case where we have the portfolio, the true returns are generated under ER process and their moving average process and their Gash model. And we do that for 1%, 5%, and 10% value at risk. Of course, that's a lot of tables. And we do it also for the scenario. We repeat this for the scenario where the true distribution, the true distribution of the error term is other than normal, either mixture or student, and the case also where there is no measurement error. So, you know, I think going through all the tables will be almost, you know, take time, but just a bit of, so for example, for this case where we look, I mean, this is the well-specified case. So we know the distribution of the measurement error. So what we have, so this table provides the bias, standard deviation, mean square error for adjusted value at risk. So our approach for different bandwidths and for different sample size, right? And we compare it with the unadjusted one. So bias, standard deviation, mean square error, again for different sample size. So what you see here is that, I mean, our approach, of course, it doesn't work for all the bandwidths, but there are some specific values of the bandwidth, in particular like 2 and 2.5. You will see that if you know, we do much better in terms of bias compared to the unadjusted one, in terms of standard deviation, in terms of mean square error. And that's for all the samples. So if you compare these values here, we do perfectly well. And that's not only for ER. I mean, you take ER, of course, I do here, I do this for ER1, but MA2, the same picture. Again, if you compare these values here for 2 and 2.5 and Gash, etc. And that's for 1%, so 99%, for 5%, which is 95%, and also 90%. Similar results. So that's what I summarize here. So so that's what I summarize here. I mean, considering the bias, our estimation approach, particularly for these two values of the bandwidth, dominates the unadjusted one. And that's also, and not only for the bias, but also for the standard deviation and the mean square error. For the case where we have the error term, measurement error misspecified, again, you know, I could go a bit fast to that one too. I think that's, yeah. So for example, for like when it's, when the true one is student, so again, you see for these two values, we dominate the unadjusted one. So even if the measure, even if you misspecify the measurement error, our approach still doing very well. Of course, for some bandwidths, but the good news is that these bandwidths, they work similarly for all different cases. And then the third one is when no measurement error case. So like there is no measurement errors, but then you use our approach. So what happens in this case, so the performance of the adjusted and unadjusted approach when the measurement errors is not present in the data. So what happened is that what we see is that the unadjusted estimator does bit better than our approach in terms of bias and mean square error, but we do, I mean, especially for these two values, we do slightly better in terms of the variance. So generally speaking, you know, this approach can be considered even when you misspecify the measurement error distribution, and also there is nothing or no big things to lose, even when you don't know. I mean, you use our approach and there is no measurement error, so you still do you still do okay. So now I'm going to move to the empirical application. So the empirical application, we consider high frequency tick by tick trade prices for 5 indices. So the French index, the German one, the UK, and the US market. So we have, as I said, so high frequency data from 2000 to January 2000 to December 2017. So we went. So of course, here we need to calculate or estimate the variance of the measurement error. So we use the approach in Aitzahalia to estimate the measurement error variance, and then we do our approach, and that's what we obtain. So I should mention that we standardize the returns just for comparison, for fair comparisons. We standardize the returns for all the for the five indices. So what we find, I mean, what we find, so for the so we provide the estimator for the adjusted approach, which is ours, and the unadjusted one that I showed in the simulation. And so what you see is that the adjusted approach tend to have in absolute value a higher value at risk, either for 5% or 10%, than the unadjusted one. So for example, for 5%, you see that in absolute value, for all the for the 5 indices, our estimator is bigger in absolute value than the unadjusted one. And that's also the same for the 10%. So that's again in line with what I said at the beginning when I said that this approach can underestimate, I mean, the unadjusted approach can underestimate the risk. And so we can see it now in the empirical application. So that's it, I think, for the empirical application. So I'm going to take a few seconds to conclude. So we develop a semi-parametric estimation approach for value at risk when the stock prices are contaminated by measurement error. We use Monte Carlo simulations to examine the performance of our approach in the presence and absence of measurement error. And we apply our method to high frequency data to estimate the value at risk of 5 international market indices. Thank you very much, for your attention.
Thank you very much, Abderrahim.
My pleasure.
Interesting presentation, and you present the difficult stuff so clearly and so interestingly that you keep our interest and looking through the innovations. It sounds absolutely easy when you are going through building it up from a simple model that has the observable and the unobservable component, and then the error term, and then working through explaining why it matters to understand the unobservable component, and then going through, you just take the simple, AR. You take then an MA, and maybe you could also, have a combination of AR and MA, which is the AMA. I guess if it is integrated, it causes problems if it is ARIMA. And then you then build on to a gauge process for volatility clustering.
Indeed.
Absolutely interesting. And then the applications. And as you are walking us through the whole process, my head was completely working through, say, for people interested in the applications, it would be on applying this to market microstructure problems, for example. like some of the work that is being done by colleagues who are here on interbank market microstructure issues. We had actually an interesting paper last week, I think, in we were looking at the interbank market in the region, in one region in Africa. And again, you know, this is where these applications can play an important role.
Correct.
Yes, one could go in even and explore, you know, like in, I think you have in equation 10, you are just tying these arguments down with the AR, with MA. You have 3 equations, I think, there, and then with the a gauge process. I guess you could even extend it to nonlinear gauge. Okay. Yeah, because that actually makes it, you know, resonate with what is, you know, kind of standard literature, and therefore, you know, take it from there. So you could just say a combination with a combination of model 1 and model 2 possible. This would be AMA, maybe with an integrated component, that would be a RIMA. Then maybe with extended a bunching process, volatility process, extended over E-gauge, tag-gauge, and various combinations. You are actually exciting our interest in the applications of this work. And even in the methods of model evaluation, trying to see, you know, why it works, that the simulation, you know, stochastic processes. I
think I mean, it's a good idea maybe to try apply this for asymmetric gauge, as you said, like nonlinear gauge, and to see, because that's quite important. I mean, asymmetry, it's quite important in the data.
Okay, absolutely exciting. Okay, shall we? Let me see whether I have any questions in the chat room. Okay, so maybe here we can take some questions.
Sure.
Please raise your hand, and I can see my good friend Bo from Linping University and African Economic Research Consortium. Please go ahead, Bo, and unmute and ask your question. I know this is one of your interesting areas of work. Yeah.
I have 2 reflections here. The first, in our practical work, we use normal distribution, and we know it's going to underestimate the fat tails. But in practice, you can adjust for that by simply multiplying the value at risk by 2 or 4, whatever. So then you think you're on the safe side. So do your model shed any light on this? Are you better than a rule of thumb here? If I'm going to lose 1 million, well, just multiply it by 2, and I prepare to lose 2 million.
No, I mean, I think that's what I mentioned at the beginning. I mean, so fact, here, if you look at this equation, I guess you can see the equation here. So the normality of this guy, of the measurement error, will have no will not, assuming normality here, it doesn't mean we will have this guy, the unobserved return, or the observed one normal. So what I'm saying is that this approach is still very general. You can have the observed return or the unobserved return non-normal, because I mean, again, this is the convolution of, I mean, for example, the unobserved return, it's the convolution of, I mean, this guy here is the convolution of the observed return that is completely non-parametric. So you see here the distribution of the observed return is non-linear. I mean, it could be non-linear. It's non-parametric. And so because of this, and so when even if we combine this with the with the normality of this guy, we could have this guy anything other than normal. So I hope it's answering the question.
Yeah. Yeah, but my other thing is that in risk management, also we look for some extreme values somewhere in the tail. So you look at the quantiles and you're looking for somewhere in the system, there might be a signal that tougher times are coming and the system might become unstable. So that would be, again, coming back to the gauge function perhaps and the asymmetric thing, and perhaps, yeah, somewhere look for a tail event somewhere in the system.
Yeah, I totally agree. I mean, you could, yeah, I mean, one could consider other processes, as Victor said, other than the ones that we considered, like ER and MA. You could go with more exotic distributions or more, like asymmetric gauge, and that may allow for,
or some threshold gauge, perhaps.
Yeah. I think you can do that here. Yeah. I think we can still have a good estimate of the value at risk even in this case.
Yeah.
Yeah, and I think thank you both for raising that question, and also Abderrahim for providing that way of trying to configure and find a way around it. Just as Bo was mentioning that it's just now, I could just remember that when the VAR model was introduced for application to banks, okay, because banks were holding portfolios of assets, and some of them were called toxic after the global financial crisis. Indeed. Where you had foreign exchange trading, derivatives holding. So the metrics of in the portfolio, okay, would be used, and then in fact in a standard VAR application to banking, you always have that question. How much do you multiply? My friend Kent Matthews says, by 4, as Bo says. I never use by 4. I possibly use from 6 to 10. And I don't know which one to use. So we have there maybe a possible extension of this, and I was about to ask the omega, the W, the weighting. Maybe something could be done as developed as part of the weighting. But yeah, there are still some unanswered questions, which possibly this theory and the construct of saying, the contamination in the observable part, that's where the problem arises, may help us get together in getting closer to, what factor shall we use when we do the VR and you calculate the value? What factor can you actually translate and say, the bank is at risk, the bank portfolio is at risk, taking a combination of balance sheet items, and then the contamination comes from the non-balance sheet items. Okay, and then you are working the value at risk. I suppose
an alternative way to also, so that's what I mentioned at the beginning is, I mean, and that's what in fact we are extending this, is you could also consider, because you are right, I mean, we made, because that's also related to what value we should take. Is it 5% or 10%, or and maybe one way to answer this question is to consider an average, and that corresponds to the expected shortfall. So the expected shortfall, you take all what is down of the quantile. So it's more, it should capture more the risk, the real risk. But I agree. I mean, the banks, I mean, we saw it in the financial crisis, where the bank, they were just selling, buying the toxic mortgage, right? You remember, from people without unemployment, they get mortgage, and they take these assets and buy it and sell it to people, and so So it's quite, you know, I agree with you, Victor, that we should multiply that by 10 because these guys,
yeah, because
they are with our money.
Yeah, Bezo didn't help us at all. What Bezo did is that, okay, value at risk will produce a new tool that will both do the computation. And then, you know, the process started. Yeah. But the contribution this work does is actually to unpack the key elements of VR. Maybe we can come closer. And the work you mentioned when you are extending this to expected shortfall is certainly would be absolutely helpful. This work is all important extension of simple risk measures that had been in vogue in the literature for a long time, where people were using the Z scores, modified Z score and so forth. I think the work has moved on, and this is taking us to important new dimension. It's also the rigor of this paper that helps us to understand these issues much more clearer. Yeah, I think there is another hand. Let me see. Or this another hand from Bojo. Or do you want to come back, Bojo? There is a hand.
No, I'm okay.
Okay. Any comments, questions from the participants? I don't see any other hand coming up. Questions, suggestions, points of views. Men, can you see something that I don't see? No?
I think I spend a lot of time going with the, with the details, and so.
Yes.
So possibly I made it very simple. So.
Yeah.
But please, if any question, I'm happy to answer.
Yeah. And maybe one question. I remember possible it was Ariel Parks, Harvard, who asked me, where do the innovations, where the changes in these variables come from? And my immediate response, the exogenous, basically. Now, a similar question would be, this contamination, the contamination in the, because that's the important, part. I'm trying to figure out what examples I would give here. If you say, yeah, of course, it's the it would be try to understand the observed value and say where do they come from? What's the is it possibly possibly the influence of like transaction costs? What are your assumptions on this? On
I mean, I think we, the theoretical, concept here is quite general. Like, I mean, so we try to, like in similar way as we do in economics, when we say that there is a contamination in the data. And of course, in the context of price, I mean, we could imagine many different sources of this contamination, but some that I mention here could be like non-synchronous trading, could be rounding errors, infrequent trading can cause also some problem in pricing. And of course, the market microstructure noise. I mean, the famous market microstructure noise in the high frequency data could be manipulation. So, could be different sources.
Yeah, this is absolutely helpful, and I agree with you. We had had a session with the colleagues this morning when we are looking at behavior in the London Stock Exchange compared to the Chinese stock exchanges, and looking at especially the behavior of the stock prices, and yes, things like the presence of state-owned enterprises in China's companies basically mean that there is corporate governance manipulation in terms of the way the evolution of the stock prices, and hence the data generation process is different from the one, say, when you are looking at prices elsewhere. So this is a very good, actually, basically one could pursue one of these application of this methodology on purely the basis of, say, whether it is infrequent trading, like the stock exchanges in emerging economies, for example.
Yeah, exactly.
And of course, in terms of market microstructure, again, the price discovery process is not so, straightforward.
Yeah, right.
And government ownership of companies,
yeah,
especially in the corporate governance issues, could lead to a manipulation of our prices and revenues and so forth.
Yeah,
so
exactly.
Thank you
I mean, exactly. These are very good examples. I mean, anything that we can, that could affect the efficient price. I mean, the efficient price is what I call efficient price is the price that should be determined by the truth, by the market, by you see what I mean? I mean, anything. I mean, of course. I'm not talking about bubbles here, but anything that can deviate from the efficient price could be due to manipulation, could be due to, as you mentioned, the examples that you mentioned, etc. So, and I think that can affect. I think that can affect the security or safety of banks, and also our saving. And so I think that's I think we need these techniques to how we call it, uncover what is covered by the business.
Yeah, and then absolutely, I can see extensions of your paper. I don't know how close you are to getting it, published, but or whether a working paper is, available. If not in Durham, maybe in Liverpool in your new home.
Submit. It's currently revised and resubmit.
Okay.
I'm very happy to share, the paper with anyone that wants to look at it or to more details, and more than happy also to have a chat with anyone that wants to use it for applications. And
so thanks for that offer. Definitely there will be people asking Meng or myself for
no
a copy of the paper, and that's thank you for making it available for sharing. Either people who want to build on this on the theoretical foundations, and then do a lot of econometric work with it, and then applications, or some the new literature emerging whereby researchers are taking these mainstream kind of structured kind of models in the literature, especially in finance, apply them and then compare them with machine learning counterparts output, because this would be actually say I haven't seen actually something like that where they are talking like VAR, okay, and these are kind of methodology applied. There is data, and the data generation process you use was able to generate even 5,000, maybe using a random number generator based on a mean and a standard deviation, then you generate and then do a stochastic, and then see the performance of AR, MA, GACH, and then number 4, the machine learning algorithm. And then you have a paper. I think we're gonna do another paper, and then maybe with the
I think this is a very good point, because I mean, the machine learning, you can capture a lot of non-linearities. I mean, I think that's the usefulness, I mean, of this approach, and you can also combine that with the big data, and yeah.
Yeah, I know that yourself and Prosper Donovan have been checking out these papers like manufacturing machines practically. So yes, I think there is a great extension, on this work, definitely.
Totally agree. Yeah.
Good. Okay, so thanks very much for exciting us and giving us an excursion into methodological issues, and we have chatted for some time on a possible extensions, and we can take it from there. Thank you indeed, and as the academic sector is opening up with face-to-face interactions, who knows? We should be able to welcome you now on the space in London or
Thanks
in
lot,
Liverpool.
Yes, and the same. You are welcome to to Liverpool. I mean, I'm quite excited to start there, and I will be leading one of the centers on big data and econometrics. So
excellent.
You are welcome, and especially if you like FC Liverpool.
Oh yes, I mean it's a great place you are joining, and started the foundations of Patrick Minford, great work there. Kadur Hadri, yes.
Yeah, Kadur. Yeah, I mean Kadur used to be there. Yeah.
Yeah.
I think he's retired, right? Kadur now, I think.
Yes, now he's retired. Yeah, but he did quite a huge amount of his influential work was done at Liverpool.
He's a really great guy. I mean, I like Kadur a lot. I mean, and his contribution also to the to the African econometric society. I mean, to the conference.
Yes, absolutely. Yeah.
He's a great guy.
Great work. Okay, good. So, please join me in thanking Abderrahim for this fantastic work.